Thank you, Chairman. First of all, thanks to all of you for still being here, sticking it out till the last day. Excellent. I'll try to show you mostly pictures, so relax. We start with the new positive tone of voice picture of the University of Warwick. We have now guidelines on how we should talk. We should always project a positive image. And this is apparently something that projects a positive image. So it has nothing to do with the content of my talk, but it will appear on all the slides. So in a Zen-like state, if you want to relax and just concentrate on the picture, I can guarantee a positive experience. I'll continue with thanking Klaus for inviting me to come over here. It's been roughly 10 years since I was last at sort of this institute. At the time, it was still in Brasilia. And I just thought back, it's also been roughly 10 years since I gave a talk on quantum Hall. So this is a fresh talk. It still has some rough edges, but let's sort of bear with me. Furthermore, I should clearly mention my good friend and colleague, if I can turn it on, Josef Oswald from the University of Leoben in Austria, with whom all this work was done. So if at the end of the talk, after you've seen all these lovely pictures, you're terribly interested, then you'll see most of the work can be found in these recent two publications by Joseph and myself, and they're based on some older work that sort of have accumulated over the years. So what we've heard at this conference thus far was basically various systems in which particles started to interact. If you look at sort of the nuclei, then clearly the nuclei sort of build up a confined region in which the neutrons and the protons are inside, and people are interested in sort of what does this bunch of interacting particles do there. When you look at the quantum dots, you basically build yourself an artificial region in which you can confine charges. And then you look at, again, sort of what do these charges do? You have sort of Coulomb effects and all this. And in these quantum gases, something very similar you do, right? You cool it down in little traps that you have in the trap, a bunch of particles, and you see what are they going to do, how are they interacting, sort of this hydrodynamic fluctuations and all this. So for many years, and I hope I'm not speaking to an audience that has completely forgotten that, the quantum Hall effect provided the paradigmatic example of an interacting quantum any-body system. Why? Well, the idea was that if you put an electron in a strong magnetic field, we all know what happens. We have the classical Hall effect. By the Lorentz force, the electron gets sort of pushed to the left. Actually, when I use the right-hand rule for the Lorentz force, I make a sign mistake, I know, because electrons are negatively charged, but the electrons get pushed to one side. There's a Hall voltage that builds up. And when I then increase the magnetic field further and further, I'm getting into a situation where this sort of motion becomes so curved that eventually the electrons go around and inside the sample find themselves back. They form a circle. And then what basically happens is, just like when a proton captures an electron and they try to form a hydrogen atom, the electron is being caught by the positive nucleus. It then goes around, it starts to interfere with itself, and it is there. And the same happens sort of with the electrons in the quantum Hall situation. You crank up your magnetic field strongly enough such that you actually get sort of cyclotron motion. The electrons go around with itself, and they're beginning to show quantum effects. So what we have is the sea of these Landau level particles that sit in these semiconductors and then move along in these semiconductors. So in that way, I'm trying to sort of explain to you who are not quantum Hall physicists, and many of you are not quantum matter physicists, that we have an interacting quantum many-particle system also in the quantum Hall situation. So this is, of course, a famous picture. What happens in the quantum Hall when you look, for example, at the resistance measurements, the Hall resistance or the longitudinal resistance as a function of the magnetic field. And in my talk, I will concentrate on the integer quantum Hall effect. And we get integer plateaus. Here, for example, the Hall resistance is 1 over an integer h over e squared. Right? So this is a standard picture. I think that many of us show when we sort of talk to the students and teach in our solid state courses. The explanation for many years has been based on actually non-interacting electrons. And when I said we have the sea of interacting electrons, this was sort of reserved to fractional quantum Hall. Now let me give you the standard picture of how we explain the integer quantum Hall effect using non-interacting electrons. So the main idea is basically we have Landau levels, which I show here. Landau levels are separated by h bar omega c, given a magnetic field and sort of some effective mass in the semiconductors. And for most of what all I'm talking about, I will use effective mass parameters and show experiments for gallium arsenide sort of semiconductors. And then the conductance that you see here, XY, transversal and longitudinal conductance. The longitudinal conductance, when you hit one of the Landau niveaus, it shoots up. There's a transition in plateau between the transversal conductances, which goes from one E squared over h to the next E squared over h value. And in between the Landau niveaus, there are no states, and hence you have a gap, so that the famous Landau gap is opening, and that famous Landau gap results in zero conductance, sigma xx, and of course plateaus in sigma xy, which is the same plateaus that you see here in the Hall resistance. Okay, and then the other thing is that for many years it was a bit of a question, why is that so stable? Why are the plateaus so stable? And here the idea was, in any real semiconductor you have disorder. The disorder should destroy this perfect behavior. What really happens in disorder here is, when you look at the density of states a bit more closely, you will find actually the disorder changes the character of the states, such that in the tails of my Landau niveaus I have localized states due to quantum interference with the disorder potential. And hence, when I have a gap in between, I have no states because I have an energy gap. And when I have in the tails of these Landau levels, even if they're broadened by disorder, I still get no transport, because unfortunately these states, which are labeled here red, they cannot contribute to the transport because they're localized. Right? So this is the standard explanation why these plateaus that I observe are so very, very robust. Because A, there are no states, that's fine, or B, even if there are states, they cannot contribute to the transport, the plateaus will have to stay there. So it's a very funny situation in which the disorder in the system makes your measurement signal even better. You get better plateaus by having good disorder in the system. Right, so when I prepared the talk, I realized, of course, that many of you haven't thought about quantum Hall for a while as well. So let me explain roughly where does these transitions, where does this actually come from? And in here I sort of hinted it already. I said states in the center are delocalized, whereas the states outside are localized. So how can I explain that? And the standard picture is now inspired by a Natal surfer. And it was not Natalie, it was just a Google surfer, but from Natal. And so the standard picture is the following. I have here these orange height fluctuations of some random potential. And then I start to fill up these height fluctuations. So this is like one Landau level, which is disorder broadened across the space here. And then I fill up these fluctuations by increasing slowly my density of electrons, for example, by an outside gate. And if you see over here, then what is happening, originally the electron does the cyclotron motion with a cyclotron radius given by that sort of famous formula, also called the magnetic length. And then on top of that, there will be sort of some bias voltage, and hence the actual motion is not the electron just nicely circling around, but following sort of this cyclotron motion along equipotential lines. And equipotential lines are basically exactly the beaches between the lakes where I have the electrons filled and where the hills come out of the sea. So imagine you're a surfer. That's why I say surfer. Surfers don't go out in the ocean, and they don't go out in the hotel. They're always at the beach, right? Because that's where you find the surf. And in the same way, here the Landau electrons, they surf around. Initially, when the filling is very low, you see you have disjoint little lakes, and they go around the disjoint little lakes, and hence no overall current comes through. The electrons cannot go all the way through the system. Then you increase your density, you put in more water, more density of electrons, and you see there is a critical value where actually the surfer then can go across the whole system, which is over here. But then if you increase the density even further, since you're a surfer, you're restricted to moving around the beaches. You see now you're in a situation where you basically have disjoint islands outside the sea of electrons, and the surfer going around is constricted to just moving around the beaches as well. So this was clearly a classical picture and a very sort of rudimentary picture of how you can see that at a particular density you have a path that goes through all the system. This is the quantum percolation picture of the quantum Hall situation, which has to be taken with a big grain of salt because the standard quantum percolation leads to wrong exponents and all this. But it gives you sort of a little picture of how you can take it, sort of a take-home picture of what might happen and where the interactions don't play any role whatsoever. So this is the standard picture. Okay, now quantum Hall physics sort of basically stopped in the mid-1990s, but since then, every once in a while, little papers come out which they do quantum Hall physics, and they say that this non-interacting picture that I've just shown isn't quite right. There's something that you can't explain with a non-interacting picture. For example, this was at the early 2000s, where measurements as a function of density and magnetic field of the local compressibility in these gallium arsenide samples. And they saw that there were particular regions here right at the plateaus where you had stripes, and these stripes were perpendicular to sort of how the plateau itself, the center of the plateau, would rise. And here just see a blow up of one of those regions. So you see failing factor 1, 2, 3, and 4. And if you were to do that and try to understand that with a non-interacting theory, and this is something we did in some earlier work, is you see here the same picture. And this is the non-interacting case. And this is again filling factor 1, 2, and 3. Actually, the black dashed lines should be it. And you blow this up, or actually you can see it already here. What you actually get is not stripes which are parallel to the line, but what you actually get here is sort of a fan-like picture in the non-interacting case. And only if you include the interacting case, which you see on the right, you actually see, yes, you have regions in which we have these stripes which are exactly parallel to the slope for numerical 1, for numerical 2, and for numerical 3. Here, for example, this region I've just blown up here, and you see nicely sort of these parallel stripes. And the way for us to get this picture, we had to do actually self-consistent Hartree-Fock. So we had to include interactions, not just at the Hartree level, but also at the Hartree-Fock level and self-consistently. And what I'm going to do today is I'm going to tell you a little bit more about what we can do with the calculations based on this self-consistent Hartree-Fock. Okay, let me show you one more picture before we move on. This is a picture of the charge density as a function of position on a 500 nanometer by 500 nanometer sample, computed here non-interactingly, and here computed in Hartree-Fock. And the charge density is 1 when it's white, and it's 0 when it's black, and when it's about 1/2, it's sort of red. And what you see in this picture here, this non-interaction picture, but now computed quantum mechanically doing the full wave function calculation. So not this quantum percolation. There's no Natal surfer. This is now a wave, a quantum wave surfing. But you see this quantum wave basically does the same as before. The thin lines here, these are the height contours, the equipotential lines of the underlying disorder potential. And you see that the charge density in the non-acting case nicely follows basically those contours. And the thick gray contour that I have here is exactly the contour that corresponds to half filling, where in the quantum percolation case or the percolation case, the surfer would have gone through. Now, this quantum surfer, so to speak, still follows this line, not perfectly, but basically okay. Whereas here in the Hartree-Fock situation, you see it's actually different. Nevertheless, what you also see is, here I've drawn thin lines, and thin lines show you the screened potential, which is the disorder potential plus the induced potential due to basically two-dimensional Laplacian on the charge density. So the charge density realigns, tries to screen the disorder potential as much as possible, and then the charge density follows this thick gray line, which is exactly half of the screen potential. And again, it can go through here. This is Coulomb interaction, yes, full long-range Coulomb interaction. Now, it looks different, but at the same time, it actually looks quite similar. If you step back a little bit, you sort of see the main outline of this big patch, and you can go through, is sort of mirrored here still. It's still there. There are no holes in the thing, which there are no holes here, but nevertheless, the main thing is roughly the same. In particular, if you look at filling exactly half the red line, you see the red line is very thin here, and here it's also fairly thin. And that's interesting when you compare it to what people these days actually assume as the modern interpretation of interactions in the quantum Hall situation, namely the Shklovsky-Shklovsky-Glassman-based picture of screening. Before we explain that a little bit, let me just tell you that basically the Shklovsky-Shklovsky-Glassman picture is equivalent to just a Hartree calculation without fog. And if you do a Hartree calculation, you get this picture over here. And you see in that picture, the red regions are much wider. And these red regions in the Shklovsky-Shklovsky-Glassman picture are actually what they call compressible stripes. And if you compare it back to what we find in full Hartree fog, our compressible stripes, our red regions, are much smaller. So, quick run through to the screening idea by Shklovsky and co-workers. So suppose we have some disorder potential that is sticking out. At the edges, for example, these things stick out, the edges do confinement. So this is just the potential curve, the black line. And before I told you that the surface run around where the filling hits the black line, which would be that point here. Well, actually, I should have said they run around where the Landau level sort of goes through the Fermi sea, which is that one, which is a little bit further away. And then the picture of the surfer was for one Landau level only. Here I can have now more Landau levels in my system. For example, the second one, it goes through here, so I would have sort of two types of surfers. Right? So Landau level 1 surfer, Landau level 2 surfer. Now Shklovsky now says because of the screening, because of the potential rearranging itself due to the charges, what actually happens is they still go through the system, but then I have these large plateaus which are forming, this large spreading, which is basically these red lines over here. And they say, in these red lines, this is where I have the charge transport. Because if I'm sitting over here, my charge is 1, I've completely filled my Landau niveau, I cannot put any more charges in, so I cannot have any transport there, I'm already saturated. Whereas if I'm black, I'm at the bottom of my Landau niveau, so I cannot also take holes away from there, I cannot have charge transport there, I'll have charge transport somewhere in the middle, around this 1/2, this is where the best is, and that's where the Shklovsky picture basically says these compressible stripes should be fairly large. Okay, is that the case? Well, in the last couple of years, this is in 2014, papers have appeared in which people can now look inside a whole bar. And this particular one is when they look inside the whole bar with scanning gate microscopy. And to cut a long story short, basically they can measure the compressible stripes. This is the picture over here. The compressible stripes are the ones which there is conductance along the stripes. They are the orange ones, and they say these are much too thin to be explained by the the Shklovsky-Glassman picture. The stripes sort of are too thin. And they try to explain that, for example, here the black line is their curve, experimentally measured curve, as you cut across those stripes. And the Shklovsky model is this one over here. And you see the Shklovsky model has these very wide stripes in which the charge density changes and just the thin plateaus. So this are the compressible regions, which are fairly wide, whereas the plateaus, which in the non-interacting case are much wider, are reduced. This here is a calculation they did on the non-interacting case. You see we have fairly wide plateaus, these small plateaus are because they used a very small spin splitting, but you have these wide plateaus and then a fairly sharp rise, whereas the rise from plateau to plateau over here is very wide. And then in between is the experimental curve, which doesn't fit either of those really. So they're saying something must be going on. Non-interacting doesn't do it. The Hartree fog doesn't really do it. What does it? And of course, by now you probably realize I'm trying to convince you that Hartree fog does it. Okay, let's see. Another experiment, very, very recent, in which they again can measure in the inside of a hole bar. Namely, they take a standard hole bar and put contacts right in the middle. And they're saying, now I'm measuring a normal Hall experiment, but I'm not comparing, for example, the curves when I take between 1 and 4 and source and drain, but I'm comparing the curves when I look at the voltage drop between B and A. And what they see there is a certain asymmetry. So when the outside, the big Hall current already says I'm on a plateau, then the guy inside, there's already, the resistance is already changing, which means there must be some voltage drop already in the system when there shouldn't be one. So what they're actually saying is the bulk of the Hall bar is not incompressible, as non-interacting theories would predict. So they're saying the non-interacting theories can't be it either. So let me just step a little bit forward, show you our calculations for a non-interacting theory, the charge distribution here. Forget about this shape in a minute, I'll explain to you what it means. But basically what you see here is the charge density. You see inside, this thing is basically flat for a non-interacting system with small deviations. And if I look at where the edge channels are only outside. And hence, if I were to put contacts inside here, this should be an insulating region, nothing should be happen. And hence, this effect that they have observed that actually there is a difference here, they shouldn't be there. So this is a small smoking gun that when they're saying it shouldn't be just non-interacting theories. Okay, finally, what have we done? So, we take a two-dimensional Hall bar, and we really make a Hall bar. Sorry, this is temperatures where all the stuff that you look is coherent, so it's way below 10 Kelvin, right? So 2 Kelvin were the experiments. So these are really low temperature experiments. So now what we're doing is we try to model the situation in gallium arsenide. And we try to model it even with contacts. So we impose a disorder potential, which sort of is confining such that it's low here. We can inject currents over here. We can draw currents out over here. And then we have sort of constricted regions where we can measure the 4 voltage probes like in a quantum Hall setup. On top of that, we throw in a little bit of disorder potential here in the bulk. So we have 1 volt confining potential, so 1,000 millivolts, and plus minus 10 millivolts, little bit of disorder on top, which I try to indicate by this color change. If I just look at the disorder potential, it looks like something like this over here. Okay? And I'm going to show you later charge densities in terms of the filling factor, because the filling factor is a nice integer number. The filling factor depends on the charge density like this, so it's proportional to the charge density. So when I talk about filling factor later on, you can think about charge density if you want to. Okay, and we're trying to do it, and this is why I selected this talk, by a non-equilibrium network model. Many of you will have heard by Chalker-Coddington type network models, which are fully quantum coherent. This model is not quantum coherent. This model works at the level of chemical potentials and currents. So there is no real interference anymore. The only thing that can happen is that you have transmission and reflection. The mu's here are the chemical potentials. They can go in on 2 sides. They can come out. Very similar to the Chalker-Coddington model. But then we have a backscattering function which can, depending on the height of the disorder fluctuations, make the transmission go from 1 to 2 or from 1 to 3, or the reflection in the other way. And I put them all together in a large big network. And here is sort of the fundamental equation for this. And you see R is the reflectance, T is the transmittance. But there is no R squared plus Q squared equals 1. It's just R plus T equals 1. And our sort of switching function P just says which of those guys wins, right? If it's 0, then the transmittance has 1. And if it is infinity, then R has 1 and T went to 0. And the switching function is chosen such that exactly at half a Landau level, it does that switch. And this is based on work that Joseph actually did, but other people sort of looked at before. If you look at Polyashov-Sklovsky 95, they have a very similar formula. Fairly recently, Dambromedil, Halperin, Morf came up again with a justification for this. The fun part, so to speak, in here, and one which Ara, who's sitting there, is already waiting for, is that this is not exact. This exponential form is sort of a phenomenological fitting. And that leads to a problem which I'll tell you about in a second. Yeah. Okay, so now we have this setup of networks, and we'll send in from one side, we put in metallic contacts, we send in a current, and then we self-consistently solve this network. For example, here in regions which are yellow, we have that we are slightly below 1/2. In regions where we're blue, we're slightly above 1/2, and you find sort of these islands. You can think of them again as sort of effective potentials sticking out or being sort of below sort of the filling. And then you solve this network consistently, and you will find, if you do that, then the current that comes out here sums up to exactly the current that you send in. So this whole thing does charge conservation and all this. And furthermore, you can go to some local probes, for example, over here, and see what's the chemical potential over here. Other local probes down at the bottom, which I didn't put in because I was a little bit lazy, because I had to actually close those loops by hand, one after the other. So these loops are not open here, they're just closed. And after 5 of them on PowerPoint, I gave up. I'm sorry. Right, so they're closed, but I can put in local probes, and I can say, where is this mu? So what's the chemical potential? And hence I can go back and sort of at this point over here, I put in a voltage probe, I put a voltage probe over here or here and here, like you do in the experiment, and just measure, put a current through the system, what's the whole voltage? And out of this, I can do all the whole physics that I would like to do. And actually, it works very nicely. So I'm looking at the conductance as a function of density. I see plateau transitions. Lovely. This is done for a 600 by 400 nanometer system, a small mesoscopic, so to speak, system, and hence fluctuations at the plateau transitions are expected. Do it similar for the resistance. Here you see red and blue curves, which are 2 different contact points. And unfortunately, since this modern projector is so good that you can't see that this blue circle is filled with dark gray inside, whereas this blue circle is not, you cannot really distinguish the longitudinal and transversal resistance. But nevertheless, you can see plateaus in the resistance, which go as 1, 1/2, 1/3, 1/4, corresponding to 1, 2, 3, 4 in the filling factor. And then you can see the resistance being 0, and then jumping up here, the longitudinal one, whenever you have sort of these plateau to plateau transitions, at least jumping up a little bit. So this produces the phenomenology of the quantum Hall effect, except you can't get the universality. So normally people would say, this of course is a plateau to plateau transition. There should be a power law sort of behavior here. I get universality. But this is, in this model, dominated by what function you actually choose. And I told you before, this is from phenomenological. So I can get any universality out of this that I actually want. Okay, how am I doing in time? 10 more minutes I have? Is that right? Okay, let's jump a little bit ahead then. So let me show you the picture that was on the second slide actually, and that's the thing I'd like you to think about a little bit. Namely, this is now the filling factor in the 600 by 400 system, and I made everything which is up to filling factor 1, I made it blue. And then everything which is up to and including filling factor 2, I made it green. And everything which is filling factor above 2 and including 3 is red. And so this is now the local distribution of the filling factor. For the experimentalists want to know the charge density here is on average 2 times 10 to the 11 per centimeter squared. So again, sort of gallium arsenide pictures. In fact, you can even for the sample estimate the mobility, which is in the order of 1 million or so. So these are supposed to be very clean samples. And what is actually happening now is I'm changing the magnetic field. For example, here I increase the magnetic field. Here I change the density. And now what I want you to see is that there is quite a bit of structure over here. So what I have is I have clusters forming. These are clusters where the filling factor nearly goes to 2. Whereas here are regions where the blue still sticks out, where there are clusters where the filling factor still stays roughly at 1. And then I change my density, and you see what happens is not that this thing fills up, but what happens is that this cluster here starts to grow. So the growth is a little bit like, I should have brought a prop. I didn't, I can try. So suppose this is, now I've filled in charges all the way to filling factor 1, which is the table. Now I fill charges all the way, now I fill the other things, filling factor 2. And what happens is, so I put electrons over here, and they form in clusters. They smear out a little bit. Stay. They smear out a little bit. This is why there's a bit of a green sheen everywhere. So there's a little bit of a green sheen on top of the blue. But then they grow only in certain regions. Like in this cluster region over there, and then make it grow larger. Right? It's not like you grow and then you spread the next set of electrons equally everywhere. No, they grow in these clusters. And furthermore, which is also funny, exactly at half filling, between filling 1, the blue, and the top of the green guy, I colored these things white. So just choose when the filling is exactly 1.5. I just said do everything white there. And you see this, there is a little feature of this white stuff over here. And that is, of course, exactly those red lines that we saw before. These are, as will turn out, these compressible stripes. And they're not much spread out, but they're very close between those clusters of filling factor 2 and the cluster of filling factor 1. Now, given that we don't have much time anymore, I'll have to show you this, because that's a movie. Let's see if I can actually get it started. Unfortunately, PowerPoint, upon incorporating the movies, decided to enhance it, and that led to a completely different speed on the left movie, which is for spin up, and the right movie, which is for spin down. Apologies for that. Bill Gates probably knows why. So here I'm filling this thing up. Let's look at this. This is what we looked before, I think. So I fill up from average filling 1/2 all the way, makes it higher and higher. This is the picture we looked at before. You see sort of the blue. Now it's a bit clearer to see. You see these clusters forming and then growing together. And this is simultaneously for the spin down situation. And furthermore, down here, with this network model, I now compute those chemical potentials, which basically tell you where the edge channel or the channel transport would be. And if you look at this for some time, you can convince yourself that you see sort of one channel coming out, and then at the plateau transition, they go into the bulk, and then they go out again. You have the second channel coming here. You sort of see one and the second channel. Then at the plateau, they go in again. Here, over here, we're right at the plateau transition, and then they go out again. You see the subsequent formation of the channels in the system. So now let's see if I can actually stop this where I want it to stop. No, I can't. So let me get out of this. Am I out of this? I'm not out of it. Oh, 7.5. So apologies, this is, you don't see it even. What does it do? Oh, this is very smart again, this system. So can you, okay, well, we can discuss it here. So basically, what I'm trying to show you is, look, this has been up, this has been down, at one particular density, and now see, wherever spin up is filled, this thing has a hole. Wherever spin up is here, this thing has a hole. So the first thing that happens is that the system tries to get one spin to be completely full before it starts the other one. So there seems to be a large splitting in energy, as enhanced sort of spin splitting due to the interaction, some form of Hund's rule. So let me see if I can go back to where we were. Ding, 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 ding. So the idea here is that, schematic idea why this Hund's rule works is the following. Suppose now I'm in the situation, I have sort of, this is my overall confining potential, the black line. I have a spin split Landau level. I have blue spin up spins. I have red spin down spins. And I'm in a magnetic field where the B field is up. So it's best if I line my spins. So I see blue is downshifted, red is a bit upshifted. I fill this now with down spins. And eventually I'll get into a situation where I could put it in the lower spin here. But I could also perhaps continue up on the other side. And what our findings now tell us, what the quantum Hall situation does, is it actually increases this and enhances the spin splitting between blue and red. And it only fills the red guy when it basically has filled all the blue guys in throughout the whole system already. And so there's some form of Hund's rule over there which works in these systems. Okay, here I just show you actually the energy diagram. For example, this is the level index, the index of the states. Here I show you the filling, and spin down is actually filled up to this point, whereas spin up, the dashed line, is really empty up to that point. And you see the splitting in terms of energy between spin up, which is the blue, and spin down, which is the red guy, is enhanced when you have this stuff being filled. And if I do it without Hartree-Fock, just with Hartree, you don't see this enhancement whatsoever. Right? So I have the enhancement here. I don't have the enhancement over here. And you can convert the enhancement, this energy splitting, in an effective and enhanced G factor. Okay? And so this picture I showed you before is at a different filling, for example. You see this here, the spin ups, let's say, they're full, but there's a hole in the spin downs, and vice versa for this local Hund's rule. Since I'm now nearly out of time, just briefly flash through. One of you experimentalists comment that they are envious of the theoreticians that can turn and turn off interactions. Yes, we can. So I can show you the same pictures, how it would look like in the non-interacting case or in just the Hartree case. And what's important to just see is, remember I told you that these thin white lines correspond to the charge, so that these compressible stripes, very thin. In the Hartree case, they are much smaller, and they're also fairly thin, but basically confined to the outside in just the interacting case. But then if you just look at, in transport experiments, what you send in, what you send out, and you don't actually do probes inside, it is very hard to see the difference. Okay, I'll forget about all of this. So, conclusions, I try to show you that actually this picture that we tell quite often to our students, that the quantum Hall, integer quantum Hall, is fully explained by a non-interacting theory, I think that's, forget it. It just turns out that the physics you measure looks a lot like non-interacting because of the presence of the interactions. You have to do a full Hartree-Fock, and then you see you recover the behavior that looks a lot like it was a non-interacting system. And only if you start probing really inside the system itself will you start to see differences. And this is something people have only done in the last sort of 5 years. Next, there is something that looks a little bit like a Hund's rule. Of course, it is known that Hartree-Fock overestimates sort of these spin polarization effects. But nevertheless, we don't have a perfect Hund's rule. We still have deviations from the Hund's rule. So I think we're basically okay. And in fact, measurements of this enhanced G factor, the numbers I quoted here were 30 measurements in gallium arsenide are the level of 15 is the enhanced G factor. So it's roughly okay, right? Don't kill me because of the number, but okay, the right ballpark. And the compressible stripes that people see in the experiments are much smaller. We can only see them in Hartree-Fock. Okay, and with this, I thank you very much for your patience and your attention. At least some of you are still awake. Thank you.